Hi everybody, I'm Vince and I'm a mathematician at Cardiff University, and I work with Paul and Jenny and a few other people who I work a bit less with. And I'm going to talk about emergent behavior, which is something that a lot of people have alluded to. I'm going to talk about two specific aspects of how to obtain emergent behavior out of complex systems. That's game theory and then network analysis, and how those two things can be combined. So first of all, this is one of the first games you would study if you were to study game theory. It's called a prisoner's dilemma. And the idea is there's two players, one player who decides which row we're in, and one player who decides which column we're in. And if both the row and the column player choose their first option, which we're going to call cooperate, they both get a utility of 3. If one of them defects, the defector gets a utility of 5, and leaving the other player a utility of 0 symmetrically. And then if they both defect, they get a utility of 1, which this is often called a social dilemma. And this has been used, for example, in this relatively famous computer tournament to explain how complex systems can lead to very simple behavior. So what you're actually seeing there is a simulation of an evolution of cooperation. So what we've got here is all sorts of different types of behavior of how you play that game. And over time, what we're seeing is strategies that cooperate do well. And that's really interesting because that wasn't put into the model to start. When this actually happened, everyone was really surprised. And so it's just a nice way of seeing how something can emerge, not from a set of rules that are given, but from the behavior of the interaction agents within your system. So we used this work, myself and Isabella and Jeff Griffiths used this work to study two hospitals interacting. And hospitals were allowed to, at some point, divert patients and say, we're a bit too full right now, we're not going to take too many patients. And what we could do is, using game theory, investigate the effect of a target. And what I'm showing there is, as a factor of demand, when there's the current demand, what is the best target that will lead to a behavior that doesn't have a damaging effect. In other words, lead to coordinated behavior. And so a lot of the time you hear that hospital wars should aim to be at 80%. It's kind of plugged out of the air. Here is a way of analyzing that and seeing that actually around, for this particular system, a target of about 72% occupancy would lead to coordinated behavior. So that's one use of game theory. Another aspect, I'm not too sure how well you can see these numbers at the back, it's not too important. Another aspect of complicated systems is networks. Networks are very complicated, and Paul and a few people have alluded to this already. Here is a network. It's a social network, not in terms of Twitter, but in terms of dots being connected to each other. And you can imagine that this is a network of kids in schools saying who their best friends are. And it's a very complicated network. So if we wanted to kind of look at this network and say, who are the important people? Well, network analysis, there are all sorts of tools within that. And so, for example, I've just colored 3 of these nodes blue. And those 3 nodes are what are called the center of this network. And so those are the nodes that are basically connected the most efficiently to all other nodes in the network. In a way, if you control these nodes, you control the network, arguably. So if this is a computer network and you want to take it down, that's where you would start. You can then, there's all sorts of tools available to you in network analysis. One, which includes just looking at the structure, so trying to get a bit of sense out of our complicated network. This is what's called the spanning tree. The gentleman who taught me that term is in the room. And this just lets you kind of see the underlying structure of this. We did a lot of work, it's already been alluded to, we did a lot of work looking at social analysis, social network analysis, and in particular, a PhD student, Angelico, who's no longer a PhD student, looked into this. And one of his big things was, over time, how do we model things in a game theory sense, where our individual agents in our system are making decisions of who they want to be friends with. And so we're looking at this at a school and looking at smoking cessation. And we had 2 things going on, the behavior of to smoke or not, but also who is my friend. And then the effect of, oh, my best friend smokes and I want to be their friend, maybe I should smoke, or vice versa. And so that leads to a very nice conceptual problem, which is a link prediction problem. So for example, in this particular aspect, we got node 1 over here, and you got nodes 3 and 4. So node 1 is not a friend of 3 and 4, but if node 1 had to make a decision to become a friend of 3 or 4, what should they do? Which decision would they make? How do you predict that decision over time? There are all sorts of different ways, and I'm just putting on 3 different indexes that exist in network analysis. And we see that the pair 1, 3, if we look at the Adamic ADAR and the resource allocation index, they would be where you would go. Sorry, they wouldn't be where you go. They have a lesser score. But if you look at what's called preferential attachment, then you look at the 1, 3 link. And so these are just ways in which you can model these links. And Angelico did that very well. He actually used a modification of the PageRank algorithm, which is named after Larry Page, who built Google. Looking at how websites are ranked, and he used a modification of that to predict how kids were over time changing their friendship networks. If anyone's interested in this, there's all sorts of tools that allow you to do this analysis. The ones I like are in Python, and there's all sorts of tools that are just there that allow you to do all this analysis.